Hi, and welcome to another interview for the Zero to ASIC course YouTube channel. And I'm very, very happy to be joined by Eric Schlaepfer. You probably know Eric from his recent great book called Open Circuits, where he sliced up lots of circuits and took photos. That was a collaboration with Evil Mad Scientist. And another really great project that he did with Evil Mad Scientist is the MOnSter 6502. So welcome, Eric.
Thanks, Matt.
How are you doing?
I'm doing great.
Yeah. So I've heard a few interviews that you've done before, like with the Ampower, that was number 609, Unnamed Reverse Engineering Podcast 85, and a recent YouTube chat that you had with Bill Hurd on his channel. So I would say to anyone that wants to find out more about you, and also, of course, your Tube Time US on Twitter,
Right.
which is, I think, how I first bumped into you. If you want to find out more about Eric or his other projects, then check out some of those interviews. They're really good, recommended. And on this latest one that you did, I just heard you say some things about the design of the MOnSter 6502.
Right.
That made me think there's kind of an intersection between ASIC design and what you had to do to make that disintegrated processor work. So I was hoping we could get into the technical details.
Yeah, exactly. I think there's some really interesting things that we can look at as far as the design process is concerned. I guess we might as well dig in. I think a great part to begin with the design of the MOnSter 6502 is kind of where it all started, which was me looking at the Visual 6502 project and realizing that they had already done half the work. So in other words, they had already gotten an image of the 6502 chip, which is, of course, closed source. So it's not like you can just go out there and download some open source schematic. But they took those images, and from that, they were able to reverse engineer all of the transistors and how they were connected together. But they did so in the form of a netlist. And so this is what I have up on the screen here. It's just some JavaScript, and it literally has a list of transistors along with the nodes that they're connected to. So it's not a schematic, it's kind of this intermediate file here. So you can see that there's this list of transistors, and then most of these numbers here, the first three are the net connections for the gate and the source and the drain. Actually, technically, they're both channel connections because they have all common substrate.
Okay, so this is a list of all the transistors then?
Yes, and then the next couple of parameters are just geometry and things like that. So it displays nicely on the Visual 6502 website. And so I kind of started with this, and I began writing a program to take that and then turn that into a CSV file that I could then import into a spreadsheet. And so for me, it was just a more natural way to kind of work from things. And the spreadsheet looks like this. And so there's a whole bunch of rows here. There's actually one row for every transistor in the design. And you might notice that these are all highlighted in yellow. And the reason they're highlighted is that as I went through and translated this into the Altium schematic, I would highlight each transistor as I completed it. So I went through this completely manually, converting it into a schematic. So 3,510 rows, not including the header row.
How long did it take you?
This took about 6 months. So it was roughly 6 months to work my way through this list, one transistor at a time, and translate that manually to the
10
schematic.
minutes a day or something.
Yeah. No, it was a lot of work, and I tried to spread it out. So it's, every evening or whatever, I would come home and spend a couple of hours adding a few transistors. And along the way, I learned some interesting things about how the net naming works. So you can see that some of these names are English, others are just numeric. And as I figured them out, I actually added some names to some of those nets that weren't understood by the Visual 6502 team. There's a couple of interesting notes in here as well. There's some transistors that are duplicate. And this has to do with the way that they turned the mask images into a transistor list. And they did that kind of with a software approach. It was semi-automated. They had some humans in the loop as well. But there's mistakes in here. They don't affect the simulation because if you have two transistors connected in parallel, the simulation works identically. There's no change there. And so these were all duplicates that I was able to get rid of. There's also a couple of rows in here. I think these are highlighted in green. I found some earlier. There we go. These are actually just ESD structures. And so they're connected as ESD clamps on the pads. And so in that sense, they're not really useful for the MOnSter 6502. And so I just left those out. And so that's kind of the whole list. That was
all
starting
the
point.
transistors you were using already were ESD protected then?
Well, they either had built-in ESD protection, or I also added some diodes, some actual discrete diodes, to clamp the voltages on the pins to either VCC or ground, as kind of the typical approach that you would see on a discrete circuit board.
Yeah. So when you showed me the netlist, I was thinking, because I'm used to like writing a bit of Verilog to describe a design, then throwing it into the ASIC tools, and then at the end, when it does a step called layout versus schematic, it's extracting the circuit from the GDS file, which is a bit like the Gerber file,
Right.
and then comparing that against the design that went in. And when you look at a gate level netlist, it's just this. It's like a big list of not just transistors, because it's with standard cells, so it's like flip flops and AND gates and OR gates, but then just wire names. So it's really, really impossible to read or take. I can't imagine being faced with that and then someone saying, "Now, can you make a PCB out of it?"
Right. I mean, technically, I could have done something like this. So I could have written a program to take this JavaScript file and then turn it into a netlist that I could have imported into Altium Layout. And I think it would have worked, and it would have saved me maybe 6 months, but it would have cost me a lot later on. It's much easier to troubleshoot a design when you have an actual human readable schematic rather than just something like this.
Yes. And I've seen the schematics on another interview that you did, and they're very nice just on their own as a way of making it much more understandable.
Yeah, so this is an example right here. So this is a section of the ALU. I think I reviewed this a little bit with Bill, but the idea was to lay this out in a way that is conducive to conceptual understanding. I've actually seen the original schematics. Somebody showed me the original blueprints, and
Nice.
the original blueprints were drawn as a way to match the layout. And that's kind of how things were done in the 70s. Like you're designing your chip, you're working with a layout person, and you would draw the transistors and the logic in the order that they would go in on the die to assist with that place and route process.
Yeah. It's one of the big differences you see when the automation came much more in, as you get like these just giant blobs of standard cells,
right,
compared to an older processor like this, where you can see the structures of the chip really clearly differentiated.
Yeah, it's a very different strategy, and you can kind of tell by looking at the die photo how the transistors are placed, where it is not anywhere near as systematic as a modern logic design is, right? So you would expect to see your VCC, alternating VCC and ground rails and all of that with the logic in between, and that's not the way that things are done on chips of this era. Everything was hand optimized and crammed in as tightly as possible, because if you could fit more logic on a chip, then you could potentially make more money from it, right? The more complex that you could fit into a single device, then the more efficient it was. And so that was kind of the idea there. But the result is that you can't really use that original blueprint as a useful schematic. I mean, you can, it just takes extra cognitive load to look at it and understand what's going on. Whereas here, with every transistor drawn out, even though it's transistor level, not gate level, you can kind of look at it and realize that, oh, we've just got some NAND gates here and some NOR gates and a couple of 3-input gates and so on and so forth. Like, it's not terribly difficult to understand what's going on.
After you stare at it enough, you kind of pull out what the cell is being created. Because I'm used to more working at the standard cell level, so I kind of recognize a little bit of the different standard cells. But I'm not really, and I can tell you where the transistors are in a standard cell, but I'm not used to seeing the schematic like this.
Yeah, and even in the 70s, this would not have been typical. If you look at the original 6502 schematic, which I've seen, and you could find similar ones out there, it's not like it's that hard to find. People have digitized some of the mask licensees schematics, which are similar, What they'll do is they'll draw individual gates. They'll draw inverters using the standard logic symbols, as you're kind of accustomed to seeing. Few devices are drawn differently. So for example, you might see an AND OR gate. So it could be like two AND gates stuck together with an OR gate, and they're all drawn as sort of a single symbol, all stuck together with no wires in between. And that would represent a structure like this right here, which is just made up of 3 transistors. And so there's some interesting sort of composite logic gates that you can make. Occasionally, they'll draw a single transistor if it's like an open collector type of I should say open drain type of a circuit, or if it's a transmission gate. But typically, they would draw that as a gate.
Yeah. So just looking at this now, all the transistors are N-type. So was this all done with NMOS logic?
Yes, this is entirely NMOS.
So all those pull-up resistors, that's where you're burning a lot of the power then?
That's why I'm burning more power. So there's a couple of interesting reasons for that. Of course, the original design is all depletion mode load, because for the simple reason that they just take up a lot less space than a resistor. And the saturation current of a active load like that, they set it to be something fairly low. I forget what the exact number is, but it's not very large. There's a bit more current going into these devices for the simple reason that in the fan-out, I have to drive all this input capacitance of all these power FETs. And these literally are power FETs. These are meant to be used in very small power supplies. And so the gate capacitance is fairly high. I did a lot of work in part selection to try and find the lowest gate capacitance I possibly could. And it's low for a power FET, but it's still much higher than a typical transistor that you would find on an NMOS device like this.
Yeah. Why did you go for power FETs rather than something smaller?
I mean, it really was just the DigiKey selection. So I just pull up DigiKey, look through the selection chart, and then I optimized it for the lowest threshold voltage I could find along with the lowest capacitance. So I was concerned because there are a number of super buffers in here, and there's a VTH drop across that. And so that means that after a few stages of buffers without an inverter, then you'll actually get maybe 3.5 volts VOH instead of something closer to the 5-volt rail.
Okay, yeah. I think you probably mentioned it, but I'd forgotten this is all running on 5 volts.
Right. It's a single voltage 5-volt design.
Yeah. Okay. So you mentioned something interesting there about Fanout. So with the ASIC tools that I'm used to using, that's all taken care of automatically for me. So you get like a resizer that will go through and like change a 1 drive strength inverter to a 4 drive strength inverter or whatever. Or for clock trees, you have special buffers that can drive things extra hard. So how did you work out where you needed to add more transistors to gang up the extra drive strength?
Yeah, so you kind of hinted at the tools thing. I basically wrote my own tool because I was thinking about it, and I kind of grew concerned about it too because, again, there's all this downstream capacitance, and I don't have an active pull-up here. I don't have any depletion mode MOSFETs in here, which meant that I basically needed to individually calculate how many gates each of those pull-up resistors is connected to, and then calculate the resistor value specifically for that. And so I wrote a little Python program that would basically go through and take the netlist, traverse it, and then for every resistor, which implies that it's an output, it would sort of traverse the connection tree and basically count how many gate pins it was connected to, add that up to produce a total, multiply it by the capacitance per pin, and then it would look at the RC time constant as a result of that. And then I had some kind of a timing figure of merit. It's been a little while since I've done it, so I forget which number I used. But maybe it was a microsecond or something like that. So, RC equals 1 microsecond. And then for the specific capacitance, you can calculate the required resistance to target that particular propagation delay.
Amazing.
So it's all propagation based.
Yeah. So what? Remind me what speed the MOnSter runs at?
It runs up to around 50 kilohertz. And surprisingly, the speed limit is not these RC delays, as I kind of expected them to be.
Yeah.
It has more to do with the bus capacitance and the way that buses work in the 6502. because everything is effectively open drain, it means that, at least in the 6502, they need bus pull-ups. And in order to save power, among other reasons, those pull-ups are not always turned on. And so what they do is they have a two-phase clock, and on one clock phase, they pre-charge the bus. And so they basically take all of the bus lines on all of the buses and then charge them all the way up. They're not quite 5 volts because, again, all we have are these depletion mode MOSFETs. So because of threshold concerns, you only get up to, some certain maximum. I think it's maybe 4 volts. It's probably less here in the MOnSter 6502 because the transistors are different. So you pre-charge, and then in the next half clock cycle, you selectively ground the bus when you're trying to load zeros onto bus lines. So for example, if you look at the RTL, let's say you're transferring a register onto the bus because you're trying to transfer it from one register into another register. So in the previous cycle, you've already pre-charged all of your bus connections up to a logic 1. And then in the next cycle, you selectively pull some of those lines down to 0 volts. And the problem is that, number one, you need enough parasitic capacitance on the bus so that pre-charge will last from one cycle to the next.
The one-stay ones, yeah.
And at the same time, you need to be able to pull them down quickly enough that they can get latched properly into the inputs of those other registers. And that's limited by the characteristics of the transmission gates that are used to gate those onto the bus.
Okay.
And I didn't have any choice there because there's very, very few 4-terminal MOSFETs that you can buy now.
Yeah. Okay. So this is another nice little side avenue to talk about is the transmission gate thing. So maybe you can explain us your version and tell us why it's difficult to make in discrete logic.
Sure. Let me see if I can find a schematic sheet to use as a visual aid. So this right here is one of the bus switches I was talking about. This actually connects 2 different internal buses together. There's a very similar circuit that's used to connect individual registers to a bus. And basically what we have here is an array of transistors that don't really have a source and drain. They have a substrate connection that's not tied to either channel connection. It's simply connected to the substrate. And what that means is that they're inherently bidirectional devices, and they also don't have a parasitic diode that affects the channel connections. So there's still parasitic diodes that go from the substrate to each channel connection, but because we haven't tied one of the channels to the substrate, we don't get that traditional diode that you would see in a discrete N-channel MOSFET.
And the 3-pin package.
And the 3-pin package, exactly. And so that winds up being quite important. So this one right here is driven by a control line. All the gates are connected together. And so obviously we need enough voltage that we can get this to turn on. The good news is that of course, the threshold voltage is relative to the substrate, and that's relatively straightforward to get. There's some other effects like channel length modulation and stuff like that you probably remember from semiconductor courses that will have an impact on here. And so these are certainly not perfect transmission gates, but they work well enough for that purpose. Where you run into some key differences have to do with the parasitic capacitances as well as the RDS on. And so these particular FETs are fairly small. They're designed to be used for differential pairs in analog amplifiers and stuff like that. And so their RDS on is fairly high, and the saturation current limit is also fairly low. I think these saturate around 8 milliamps or so. And so all of that acts as a speed limit because when you're trying to drive the bus with all the bus capacitance, you can only do it so quickly.
And your traces are centimeters, not microns.
Exactly. So there's a lot more parasitic capacitance on the traces. This is a 4-layer board, and I have a ground plane. And so, yes, every trace has quite a bit of parasitic capacitance as well.
Yeah. Yeah. Were you able to calculate that and take it into account?
The trace capacitance, I didn't bother calculating because it's swamped by the capacitance of the MOSFETs. So both the drain to substrate and the gate to substrate capacitances.
Amazing. Is there anything else that you think is interesting about where we're at the moment you want to tell us?
Yeah, I mean, it's a really interesting design in the sense that there's so much done by hand. It really gives you a sort of a snapshot of what IC design was like before the existence of EDA tools. Remember, this thing was designed entirely with pen and paper. So I've talked to the designers before, and they said that they actually don't remember if they used simulation or not. But if they did, it would have been a timeshare on the PDP-11 or something like that running Spice. And so there wasn't really a whole lot you could do without spending a ton of money. So most of it was done with pen and paper and possibly a calculator, most likely slide rule calculations.
Yeah. Do you think that they built out little bits of the circuit in a discrete fashion, like you
Most
did,
likely.
to test little bits and pieces?
Yeah, most likely they had some form of a wire wrap prototype. And that feeds into some of the design challenges that they ran into. You know, people like to talk about the rotate right and say, oh, well, it was a bug and it was broken and all of that. And of course, I've already done a video describing why I believe it's not actually a bug. It was just never implemented. But based on
I
what I've
watched it
seen in
today
the
when I was
design,
brushing up on my 6502 theory.
right, yeah. But based on what I saw in the design was that I think they were trying to get it to work on their possibly a wire wrapped prototype or something like that. And I think it was taking a really long time because they were running into issues getting that running. And so at some point, Chuck Peddle, I think, told them, look, guys, we got to get this out in the market because the timing is perfect. We've got to get it out now. If we wait too long to try and get this issue resolved, then the market will have moved on. And so you can kind of see in the design, there's these sort of little stubs of functionality that were put in, but then disabled before that first silicon.
Yeah. I watched a great video kind of in preparation for this interview by, it was at the 27th Chaos Communications Camp by Michael Stile, Reverse Engineering the MOS 6502. Have you seen it?
Yeah, that one's excellent.
Really good one. And there's one bit where he kind of showed this, like, from the decode logic, this wire coming down and then just going nowhere.
Yeah, it just ends.
And of course, that would never happen in a modern flow because anything not connected is just thrown away at synthesis.
Yeah, exactly. Actually, that brings up another interesting subject too, because remember, when you're doing everything by hand, pen and paper, or you're doing your layout using rubylith, you have to manually check it against your own schematic. It's not automatic. So they had to go through manually. And in fact, from what I understand, everybody in the company, in that tiny little company, was involved at that point, checking to make sure that each transistor matched up and that everything was wired correctly. Like, that's your one shot, because once you're done and you've released that rubylith off to the company that will shrink it down and make the masks, I mean, that's kind of it.
Yeah, and we face the same thing today. Yeah.
One of the things that I ran into myself was a version of that problem. In other words, I had this big schematic that I built, transmission gates or ALU logic, and I didn't know if it matched up exactly with the Visual 6502's netlist. And so I ended up writing my own verification program to compare the schematic with the existing netlist.
I knew you would.
Yeah, I mean, you kind of have to, right? I mean, you could try to do it by hand, but it would be tedious, and then you wouldn't be able to repeat it easily.
Error prone as well.
Yeah, so you just have to automate it. And I actually
did catch your own LVS tool. That's cool.
I did catch 2 or 3 mistakes that way, so it was a good thing I did that.
Yeah. So that was post Altium, right? So you'd done your Altium, but you'd yet to send off the PCB.
I hadn't done the layout at that point. So I had a schematic.
So this is like pre-layout verification. Cool. Just trying to tie it in with the ASIC milestones as well.
Yeah.
So you wrote your own LVS tool, essentially. Was that another Python program?
Another Python program. I would share it, but it's pretty awful looking.
Really janky?
Yeah.
Well, if you look at any of the open source ASIC tools, you probably won't be ashamed anymore.
I did a meme on Twitter a while back. You could probably find it if you look around, but it's a fake O'Reilly book cover about crappy Python.
Cool. I'll put it up here in the edit.
Fun to look at.
Okay, so you did find a couple of errors. Great. So it's well worth writing the tool.
Yeah, absolutely.
And if you, when you do this again for the Intel 4004, then you built your own tool library.
So it's funny you mentioned the 4004, but that's already been done. So someone out there has already done a discrete 4004.
Okay. Yeah.
It's pretty cool.
Yeah. Yeah. Maybe just while we're on that topic, so I did ask for questions, but almost all of the questions have previously been answered in your excellent videos and interviews already. So I'm not going to ask them again. I just direct people to the things I've already mentioned and put links down in the description. Okay. So now you've got your, you spent 6 months and you've got a layout in Altium. Then you've got to actually do the physical layout.
Right. So 6 months in, I've got a schematic, and it's hierarchical, so it's fairly similar to what you would see in an analog IC design. So yeah. I think most
at
of
this
our
point, were you regretting your decisions?
The whole way, every moment was pain.
You told a story in one of your other interviews about like just building the program counter, and then when it worked, you were both like happy but also sad that it meant that you were going to have to do the whole thing.
Yeah, the whole process was basically me trying to prove that this couldn't possibly work and that I shouldn't attempt
it. So that you had a good excuse to give up.
Yeah. So so a lot of it would involve prototyping transmission gates. So I have a couple of breadboards and stuff where I built individual gates, transmission gates, and flip-flops and things like that. Yeah. And then the program counter was kind of the next big step. The fun story there is that I actually had part of the layout already completely done before I thought, maybe I should take a step back and build the program counter, because this is going to be a very expensive board. And it turned out the program counter worked and the carry propagate worked, which was really what I was worried about. I was concerned that there would be some maybe gate threshold issues or something like that, where the carry would propagate partway and then stop, or there might be some timing issue or something like that. But it actually worked fine.
Yeah. I guess also because you've got a 2-phase clock here. So if stuff goes really badly wrong, you can adjust those phases and you have a little bit of leeway there.
Yeah, exactly. And unfortunately, it's all interdependent. So if I adjust the clock phases, then that could throw a wrench in the way that the bus pre-charge cycle works. So there's trade-offs everywhere. Yeah. I guess I would say that's the other challenge, is that this design is, besides being fairly archaic, it's also dynamic, which is a real problem, because that means that there are dynamic latches scattered around everywhere. So we're storing our state information literally in the gate capacitance of inverters and other gates.
Yeah.
So that means we can't even stop the clock.
Do you want to just explain what a dynamic latch is compared to a full latch?
Yeah, let me try and find an actual register that we can look at that's got some dynamic latches in here.
Yeah.
So this, I believe, will work. Hold on, let me make sure. Okay, so I think that's right. That goes off to the bus. No, that loads 0. This is just a transmission gate.
And if anyone watching is interested in how flip-flops work, then I can recommend my video on that.
Right, exactly. The program counter changes every cycle, so I think that might be a pretty good example of a dynamic gate. I'm just trying to think if there's one that might be more clear. This one's okay. So we're looking at the program counter. You can kind of see there are these diagonal lines going in between each bit. So that's how you propagate the carry. Because what you're doing is the program counter can load an arbitrary value off the bus, but more commonly, it's just simply incrementing itself every clock cycle. And so that's why we have those lines connected in between. The dynamic part of it, the easiest way to look at it is right here in the middle. So we have an inverter connected to another inverter. And so this is a buffer stage. And then in front of that, we have a transmission gate connected to one of our clock phases here. In this case, it's called C clock. And what happens is that when we're in the C clock phase, this transmission gate is turned on. And so whatever data is coming from the output of this gate beforehand comes through and then gets loaded into the gate of that buffer, right? So the buffer now has either a 1 or 0, either high voltage or 0 volts loaded into it. The next clock phase, I should say the next half clock, this C clock line turns off and that transmission gate opens up. The state of this transistor stays the same because there's charge that's been loaded onto the gate of that MOSFET, and there's nowhere for it to go. It'll slowly drain away for essentially leakage currents and stuff will slowly drain it away, quantum tunneling effects, that kind of thing. But for the most part, it sits there and it just stores that state. That's a dynamic latch. So a regular latch is completely stable indefinitely in either a 1 or a 0 state, but a dynamic latch will slowly change from a 1 to a 0 as that gate charge drains away.
Yeah, nice explanation. And I guess, like, related to the design is that the designers were thinking we're designing for a specific process. Like, one of the great pictures shown in that reverse engineering was the layers. It's like 8 layers, I think they were using.
7 layers.
So very early, 7 layers. And one thing I really liked about that was it was like 7, 6, 5, 4, and then you can't read the other numbers because they're invisible, because they're like diffusion or doping or whatever.
Yeah, they're the ion implantation layers.
Yeah.
So layer 1 is the first diffusion, which, of course, you can use to build your transistors and all of that. And then the next 2 layers are the ion implantation. And that's what you can't see because, you've got your ion implanter and it's literally an electron rifle or a ion rifle. And it's just firing ions into your substrate at a predetermined depth. And so you're not going to see anything from the outside. No. But by the way, that was kind of their big innovation, right? So the process was something that MOS designed themselves, or I should say Chuck Peddle's team, when they joined MOS, because they knew the existing technologies for building chips and they knew all the limitations. So PMOS, for example, was pretty common at the time, and it was a pain to work with because you needed all kinds of supply voltages and you had to be very careful about biasing and things like that. And it was also slow, and that has to do with the or the carrier mobility, I should say. And so that was a problem. But they had been reading papers that were published that discussed using an ion implantation technique to take NMOS transistors and make them depletion mode. And the idea there is that you're shifting the threshold of the MOSFET so that even if the gate to source voltage, I should say gate to substrate voltage is 0, the MOSFET is still turned on. And so if you think of the voltage curve, the IV curve, you've got your classic MOSFET set of curves. Imagine shifting that to the left. And so now it's turned on essentially continuously. And so that's how you build a current source. And so that was their big innovation.
And they were designing this for that process. So now you're recreating this at the PCB level.
Right.
Things might not work exactly the same,
right?
Because you've got totally different types of devices and all your parasitics and everything else is all different.
Right. Yeah, exactly. I can't use a depletion mode device because they're uncommon on the board level for a board level design. And so I just substituted them with resistors.
Yeah. Same kind of story as the transmission gate.
Yes, exactly.
But luckily you had a bit of a easier workaround there. Okay. Cool. So we've seen the an example of a dynamic latch and how that works. Should we move up one level now to the physical layout?
Sure. Let's take a look at that. It's going to take a little while to come up. The file is big.
Yes. There we go. How big is the file?
That's a great question. Let me take a look.
One of the interesting things in the reverse engineering talk was that the total entropy of this design was something like 7 kilobytes.
So this is a 21 megabyte board file.
Yeah. Massive.
Yeah.
I love the way that you've got the bond pads around the edge. That is such a nice touch.
It's also very convenient for testing because I could go in with alligator clips and just connect to them.
Just clip them on, Yeah.
Yeah, so the layout is directly inspired by the original. and that helped a
Yeah, so
lot.
it's cool that you were able to keep it matching. Yeah.
Exactly. And some of it is cut and paste. So on the registers here, I could cut and paste a lot of the traces, but there's still some routing here that's fairly unique. And it took a lot of work. This is about 6 months of work to get that all laid out.
Yeah. So you were really regretting your choices at this point.
Yeah, it's a couple hours every night. I would just sort of chip away at it, but it was very tedious. Kind of gives you an
Yes.
appreciation for the layout engineering that was done by hand in the 1970s.
Yeah.
All this
Yeah.
was something you had to do with Rubylith by hand. And if you imagine making a mistake and realizing, oh, well, these all have to be shifted over, then
Yeah.
you just went in with your X-Acto knife
Right.
and,
To just
and chopped away.
slice and
Yeah.
dice. Yeah. Yeah. Wow. So you said it's a 4-layer board.
It's 4 layers. So there's a power
Yeah.
plane and a ground plane and signal traces on the top and bottom.
And loads of LEDs.
Loads of LEDs, a lot more than the original.
Yeah. Yeah. So I guess you can just use, once you're happy with the schematic in Altium, Altium has got a test that checks that your layout matches. So that level of the layout versus schematic, you didn't have to write a Python program to do that.
Yes, yeah, that's one of the advantages of using a schematic, is that you get
You
that
didn't decide to
automatic comparison.
write your own PCB design program to make it even harder.
Exactly.
Yeah. Is Altium scriptable? Is it something that you could do a bit of for the decode? Could you show us the decode
Sure.
matrix bit at the top? Because that seems like that's something that would be fairly easy to kind of programmatically create.
I didn't end up scripting that. This I just used a lot of, not so much cut and paste, but I would just set up a grid and then move things around and then use the alignment tools to get them all lined up right. So it looks like something you could use a program or a script, and I probably could have, but I didn't end up doing it that way.
Yeah. I think is also when you see it in action, or also on the visual 6502, where you can run and step and things like this, it really gives a great insight into how this processor works, where the instructions are decoded by this big matrix, and you could see how powerful that technique would be, where you're like, okay, I'm going to add a transistor here and that's going to make this line go high, and then I can use that to sneak through all the layout, and that's going to make this AND gate turn on or off or whatever.
Exactly. In fact, this was really helpful to have the access to the Visual 6502. I just use that as my simulation tool. So if I was debugging something on the board, then I could just pull up Visual 6502 and run the same program and look at some of the nets that lighted up, and then I could compare that with the actual board.
Yeah. Okay. So yeah, let's move on then. So you've done the layout, and you've did you? I guess the board it's pretty big, but you probably didn't have to go to a special fab place to get that made, did you?
Most fabs can do a board this big. It's just expensive.
Yeah.
The other challenge was for the assembly. The pick and place required several
I was going
reels
to
of the
say,
same
did you
part.
do that yourself, or?
No, I didn't do this by hand. That would have been tedious.
Yeah. Well, that would be tedious.
Yeah. Although I did swap out the LEDs when the boards came back because they had used the wrong part number, and that was definitely tedious.
Yeah. Yeah. So okay, you got your assembled boards back then. So now you're on to this final stage of verification between the intention,
right?
Which you said you can check on the Visual 6502.
Yeah, the most
and what
important
you've
thing
got in
was
your hand.
coming up with a Powerup strategy. And so in this case, I used a power supply with a current limit. And I started with a rather low current limit, and I slowly brought it up. And as it turns out, that was a good thing, because of some issues with the clock. I discovered that it was possible to get conflicting states in part of the logic. And so there was one spot where there were 8 super buffers that could actually turn on at the same time, and you'd get a shoot through current. But because I had a current limited supply, I could see that the current was very, very high. And I could also tell that the board was heating up. And since I don't really have a good thermal camera, I could get a vague idea of where on the board it was. But to kind of narrow things down, I wound up using a piece of Scotch tape. And so those super buffer transistors melted holes in the Scotch tape. And so then I knew kind of what was going on, or at least I could progress to the next step of troubleshooting. But that was kind of the basic bring up, right? So you're applying power for the first time, and you're looking for major power issues like that. And so I was able to bypass them, at least temporarily, to get more and more of the CPU up and running.
Yeah, so maybe we did miss something a few steps ago then. Did you have an idea of how much power this is going to draw when you turned it on? Like,
Not really.
What were you expecting? No, okay.
I had a vague idea, but I wasn't sure what the dynamic consumption would look like.
Yeah.
So, but I figured it would be mostly the static loads in the load resistors. So some percentage of them would be turned on and some percentage of them would be turned off. And then, of course, there's LED power as well.
Yeah. So because this is all NMOS,
correct.
When the MOSFET's turned on, that's when the resistor is drawing the current. Yeah. Okay. So what is the power draw then?
It varies depending on what you're doing, but typically it's around 2.5 amps.
Okay. Pretty chunky.
Yeah, pretty chunky.
So that when you turned your power supply on and it went way past that, you were like,
yeah, I thought, well, that's a little high.
Yeah. 2.5 amp CPU, amazing. I mean, I suppose modern graphics cards use a similar amount, don't they?
Yeah, or potentially
with
more.
billions more transistors.
Yeah.
Yeah. Okay. So you brought up the power supply. That must have been then you worked out that problem. Did it at that point start kind of stepping through and clocking its first program?
So the first task there was to essentially test execution of a no-op. And so I did that by basically pin strapping the data lines to the no-op instruction by using resistors. Data bus is bidirectional, so I can't just simply strap it to VCC or ground, because then, those might be turning into outputs, and then I'd get excessive current there. So I used 100 ohm resistors, loaded the no-op instruction, and then just had it run, just had it fetch and execute. Of course, it'll fetch the the reset vector address first, and it's just going to get the no-op instruction, which is fine. And so that's your initial program counter, and then the program counter will just simply increment, and that's what I was looking for. So I ran it with a relatively slow clock, maybe 10 to 20 hertz, and then I could look at it, and I noticed that the program counter was indeed incrementing.
Wow. How did you feel?
It felt pretty good.
Yeah.
I was still nervous that there would be some other issue. Remember, I already knew the program counter would work based on that previous test.
Yes, but having everything all together, everything all connected, must have been a great feeling.
Yeah, and then I think from there I started putting in other individual instructions. So then I would feed in like a add one to the accumulator type of a thing. I don't really remember what other instructions I used, but it was a fairly abbreviated list of just a couple of instructions to see if I could get any behavior out of it.
Yeah.
And then I would look at the instruction, register LEDs, and I would look at LEDs all over the board to try and figure out what was going on. And then I think at some point I also implemented the WAS single step circuit so that I could single step the processor without having to stop the clock.
I don't know that. Is that like a trick you can use to like build some external thing?
Yeah, it's a trick with a single TTL logic chip that you connect to the sync pins and the ready pin. And so you can cause the processor to basically go one cycle at a time. And so that was very helpful.
Old school debugging trick.
Yeah, exactly.
Single step TTL.
And then from there, I had a little computer that I had built, and it had its own little ROM, and I started trying to run actual software. I think the first program that it actually ran, at least partially, was the Apple II Integer Basic. So I just wanted some simple program that was already kind of confirmed to work. And I had already gotten working with a regular 6502 chip. And so I plugged in the MOnSter. And
is that the little board that appears in the video where it's got the 60, and you can take that out and then plug the MOnSter in with that flexible cable?
Exactly.
Nice.
So it actually came up and it executed the basic program without any issues. It just worked the first time, and I was really shocked.
Yeah, amazing. Good job.
Yeah, thank you.
Yeah, congratulations. What an incredible project.
And of
Yeah.
course, I was still suspicious because I don't believe that BASIC uses every possible instruction. And so then
No.
it went into
Yeah.
actual, somewhat more formal verification that the CPU is actually working correctly.
Hmm.
And so for that, I
Yeah. So
found,
I wanted to get onto that. So
yeah.
like, how did you come up with a list of test vectors, or how did you like make sure every transistor? Because the thing that I want to get onto, like I think probably last is I know that you're going to make this into a product one day,
Hmm.
and you've got to have, if you're placing so many transistors, you're probably going to end up with some odds and ends that don't get mounted properly. So you're going to need to have some fairly rigorous testing in the fab, right?
Absolutely.
So
Absolutely. It's the same
what's
kind
your
of
plan?
tests that you would use for an actual chip itself. And
Hmm.
what I wound up doing was pulling together a test program that runs a whole bunch of 6502 instructions. And I did it in 2 stages. So the first stage is to verify bus activity. And the program runs while there is another separate microcontroller that observes the 6502 bus to make sure that the bus cycles all look correct. And so that's kind of a
Right.
cycle by cycle verification. Doesn't verify all the inner workings of the chip, but it does verify sort of basic functionality. Stage two is a
Yeah.
more complicated test set of test vectors that, again, it's 6502 instructions, but the idea is to exercise all possible instructions with all possible memory addressing modes and carry bits and all those types of things.
Hmm.
The challenge was, so I actually started with somebody else's open source 6502 verification, and it was designed for someone's 6502 FPGA project. The
Okay.
problem was is I didn't know what the test coverage would be, and so I ended up taking the Visual 6502 JavaScript and hacking it together with another script that would go through and disable each transistor one at a time in the design. And so it did it
Hmm.
twice for each transistor. It would make the transistor either stuck on or stuck off. And then it would run the entire validation suite to see if it detected that broken
Check that it
transistor.
actually failed.
Mhm.
Right.
And so then
Cool.
by taking the
And
percentage of transistors that were detected versus the total number of transistors, I was able to confirm that test coverage was around 80% after I made some improvements to the program.
okay. So right. So you could still go through manufacture and have a few failures, but they wouldn't get picked up by the validation.
Right. So it's certainly
Yeah.
possible. It's just a lot less common for that to
Yeah.
slip past.
And if it can run all those programs, then it's going to be able to run all the programs that people are going to throw at it in everyday life
Right.
anyway, aren't they?
Exactly.
Yeah. Yeah. Yes. I guess it's probably obvious to most people, but this is like older than where I was at. What the first microcontrollers I were using had integrated program memory as well, so you didn't have that um, ability to spy on the data bus that you do with this chip.
Right.
So I guess that does make things a bit easier with this second processor looking at what's going
Hmm.
on the memory. Great. So where are you at with the production plan then? I know everyone is asking. That was like the number one comment on Twitter. It's like, have you got any questions for Eric? And it's like, when can I buy one?
Everybody wants one. Yeah, I think it would be wonderful to be able to offer that for sale, and that is our long-term plan. There are a lot of
Hmm.
challenges with that. Well, some of them are supply chain related. Of course, we are sort of coming out of a pandemic, and so that made things very difficult to get anything really designed and into production. The
Hmm.
supply chain challenges, I think, are probably a bigger concern. Some of the parts are available again, but they're much more expensive than they used to be. And so we kind of have to
Okay.
reevaluate what that price would look like. It also means that we have to
Yeah.
get minimum orders in. And honestly, the volume is high enough for some of these parts that we're probably going to be triggering wafer starts, which means that there's going to be a pretty significant lead time. And then things like financing become a concern because then that means that you
Yeah.
have to pay for all the stuff up front to get that order
Yeah.
in.
Yeah.
And so we're
Have you
thinking
ever thought
about some
about,
crowdsourcing options for doing that.
yeah, maybe you could like, instead of building it out of individual transistors, you could integrate it into one circuit.
Now there's a thought.
You could save some money that way.
Yeah, sort of a fully integrated circuit of some sort.
Disintegrated circuit. Yeah, nice. Great. Okay. Is there anything else you want to
add? No, I think that's it.
Right. Well, thanks so much for your time, Eric. Really fascinating, very interesting. We'll drop a link to all of your contacts and stuff in the description of the video. So if you want to find out more, then click on the links below, and hope you enjoyed this interview.
Thank you, man.
Thanks again.